Um, this is the part 2 simulation webinar. So previous session we have conducted in the simulation area is static analysis and the motion analysis. So you can have a look in the chat box afterwards. And now once again, so this is the portfolio that we offer. Today's session here is I'm going to cover the fatigue analysis, which comes in the simulation package standard, fatigue analysis and optimization. So before getting in, I would like to explain a few words what it is fatigue analysis here. So the fatigue analysis, okay. So as of now, we will go for a static analysis to check whether the part is getting a weak in a particular area with respect to the load. So even though we need to validate that how long the product is going to last. So when designing a product, knowing it, it is where the position is critical. However, knowing how long it will last is more important as well. So durability helps to ensure to meet the customer needs as well, minimizing unexpected warranty issues. So determine the product durability. So we have here is the fatigue analysis. We can go with cyclic loading, constant variable loading also. So here you can see the constant load, which means the same load is going to happen on the particular phase of area and how much the cycle is going to withstand the constant load. So the variable load means, for example, the lift, we can say as a live example. So one time there will be a 150 kg or another time there will be a 500 kg kind of lift. So to predict the value of the how long it is going to be, we need to check with the fatigue analysis. So which gives you a material strength variation with repeated loading or the constant loading. So here we have total life, damage and the factor of safety we can calculate with respect to the load what we are going to be applied in the multiple load cases or single load cases and all. Okay, this is the simple overview. We'll get in deeper now. Now, optimization. I'll get getting optimization it in the next when I complete the fatigue analysis. So let's go with fatigue analysis. How it is. So this is the assembly which you can see on the screen. As an example, here is a crank design. So bicycle, most of us know will everyday usage of bicycles. So still the bicycle is in the market. How it is going to be run, how it is going to be, how long the warranty period should they provide to the customers. So here I have taken a particular portion called the crank design over here. So this is the crank design which is mounted on the pedaling part of area. This is the configuration. You can see the pedaling part of area. So for analysis, I am going to take three type of crank designs. One is you can see the crank mounted over these 1, 2, 3, 4 and 5 point will be a bolting area, and this is the pedal loading area. So this is the first design. I need to check how which kind of a crank will be better life cycle and damage percentage is where and all. So this is the second type of scenario, and this one is the third type of scenario. This is the flat of mounting portion, and this is the head of head included, and with the guided shaft will be inside. So for that we need to do a static analysis first of all. So first of all we need to perform a static analysis for that. How the 1315, so like 135 kg of load is going to be acting on this particular phases in this motion, and this fixed hinge area is that 5 part of pinhole area, and this is the center arm shaft. So this is the conditions. Once it completed the simulation of static analysis, we need to perform a fatigue analysis for that. So how it is? So the fatigue analysis, which is we need to go with new study and the fatigue analysis. So here you can see the constant amplitude event with defined cycles. Okay, we can go for this. This is for variable amplitude. So what I need to go is, we need to go with the repeated cycle of constant variable. So we need to go with the fatigue analysis called repeated cycle. So once I completed here, I need to go with adding an event. So what I need to do is, I need to check for this cycle as 70 million cycles. So which means I need to go 70 lakhs, like the cycles I need to do. So this is the zero base rotating constantly in the same direction. So 0. So what is the main source of study I need to check with this? The static study 1. So here, which is the stress and the deformation data, everything will be collected from the static study. Okay, once I completed this, I need to go with the material data. So the material data needs fatigue SN curves, stress versus number of cycles curves we need to apply for this. So once I completed applying, I can go and run the study. This is for the fatigue analysis procedure. So we can go with three different set of scenarios here. So first one, this is previously solved one. So we can go and check with the result plot. So once I completed, simply I need to run the study as I have said with the procedures. Okay. So once it's solved, okay, here you can see the value of event 1. I can show you with edit definition here as I mentioned. Then once I solve this study, I can go and check with the damage plot area. So wherever in the static analysis, we may have a high stress value in the particular region somewhere in this part of area, but we need to go with the life cycle analysis to check the 70 lakhs cycle where will be the stresses happen. So we initially the static analysis will show one portion will be the stress acting point of area with respect to the load and the conditions we provided. So only we go with the fatigue analysis with number of cycles rotations only. The stress will vary from the one location to another. That indicates the damage which occur first. So here in this design cycle, the damage will occur first in this particular point of area, and we can see the life, how much life. So 3960078 cycle will be the minimum cycle for this crank design. We can check with the value for the life. So instead 3960078 value, roughly we can take it 1 day cycle rotation will be a 1000 number of cycles, means into the divided by the 1000, how many number of cycles per day, like that we can calculate the value. So and we can go with the study 2 with configuration 2. So the same load is getting happened here as 1350 Newton, and the same static study design 2 as well 1350, and the setups as the same, and all the setups are same. So for that, this design I need to check the damage where it is. So in this, the damage happened at the bottom of the area. So stress wherever it may be, the damage will be occurring at the starting point. Starting damage point will be this particular portion. So why this portion? We have changed the design. So with respect to this, we can go and check with the life. So you can see the life is tremendously increased. So the life cycle value is 13 million something it goes. So we calculated with this design scenario 2 is better than the design scenario 1. And okay, and one another study is here. Okay, same setup has been copied for this also. So and the design is varied. So the width of this crank is varied, and the thickness of the mounting point of area is also reduced. So with this, what we need to do is we need to check with fatigue analysis for the same. So for this, where the damages happened, so the damage percentage is occurred at the corner point of area. Previous one happened on this position, that is the percentage value is less. Here is the percentage value is 516. Okay, this is the scenario. In this scenario, I can see how much the life. Okay, with this we can predict the which one is the best design and which is the highest life cycle we can achieve, and the damage percentage should be also lesser. So design 2 damage percentage is 51% only, and the design 3 fatigue is more than 100. It is around, the damage percentage will be around 506 damage percentage will may occur in the particular area. So with this results, we can predict that the damage percentage and the total life will be, the design 2 is the safer one, and the more number of life will be in the design 2. Okay, I hope this is more informative, and this is one of the very much useful tool for manufacturing of a part in terms of a quality. This is in the fatigue analysis part of importance here. Then I will go with the optimization. So we need to check the design is over design or the design is under design. So how we can do? So we need to go for number of configurations in the static analysis. So instead of here in SolidWorks simulation, we have a design optimization tool which you can find a best alternate design, let it software do. So we don't need to bother about that. We will do only one thing. We need to give a the value of minimum and the maximum of the geometry thickness or the height or width. So once we did that, the software will automatically calculate the number of iterations, and it will find the best alternate scenario. And the main what is the main advantage here is it is reducing the cost, and it don't uh, don't complement with the product quality. So the material also getting reduced, manufacturing cost is reduced, time is reduced, and the quality also improved. So this is the best thing the optimization tool will do. So let's see how it is going to do in the live example I would show here. Okay, let me close with this. So I'm opening up with an assembly which contains 4 number of parts. So it is an example one. So initially the design study, how it is going to do is we need to do a static analysis before that. What are all the conditions we are going to provide? For that only we are going to derive the optimizations variables. So here you can see that this is the value. We need to define the variable over here. So for that, this is the one of assembly where it contains 4 number of parts. So this is the default configuration. So what I'm going to do is here here the value is force. It is going to lift at the top of the point is 2268 kilogram. Okay, so the 2268 kg force is lifting towards the top. One second, I will show the force. This is the force uplifting. This is the application of the assembly. Once I done this, so the force applied and the fixing point is at the bottom and solving, and we are getting the results over the conditions what we provided, and the displacement plot also is the 0.5 maximum with this point of area. So I need to do a analysis of optimization where it is going to, so we can go with new, and the design study is called the design optimization logo. We can take it. For that, once I completed, the design study will appear here in the bottom near the statical motion. So once I done, so I need to do, what I need to do is here, this is the geometry based optimization. So it here the range, previously you can see here is the solved one. I can do the new one. Here is the back range. I need to do is minimum and the maximum range. The range should be the, which one is 50 to 100, the back side of the plate. The back height of the particular plate is the values 72 now exactly. I need to reduce or increase with respect to the strength. Here, for that I can give the value called 50 to 100. Maximum is it goes 100 and minimum it goes to 50 with respect to the assembly, and also feet width, so 100 to 250 mm. So the width is 100 to 250 mm I can give, and the plate length should be 150 to 375 mm. So this length should be, minimum of 100 and maximum should be 375. So within the limit I need a better design for that. So this is one of the variable in terms of the geometry conditions. On the constraints, so the stress factor I need to consider that. So the stress should be minimum 100 Newton per millimeter square. So where the source study is static analysis which I performed, I should done the static analysis before taking the optimization if I need to get into the simulation constraints inside the optimization part of area. So for that I need a stress constraint, I need a displacement constraint, and I need a displacement constraint is 0.5 and 1. This is the displacement 2 and displacement 1. So for that you can see here the displacement 2 and displacement 1 will be the resistance displacement is maximum how much I can see. So this is the 0.5 maximum occurred. So I need maximum should be 1 and maximum or should be 0.5. This is the value where I can give. So the main goal I need to do the optimization is to minimize the mass. So the main goal is to minimize the mass. That should be a better thing for cost reduction, return of investment, everything. So in terms of manufacturing. So once I completed, the view will be, the software will automatically taken into the scenario. So the initial design will be as like this. So this is the initial design, and once I run the analysis, the software will automatically take through a multiple of scenarios. So optimal 1, optimal 2. So what the software does, so initial one is, so I can change this. So this one is 100 mm of the back height, and the feet width is 250 mm. It took one scenario. So let it solve. So what it solved is, the software will multiple scenario is going to solve. So at the time of 50 and 250 it took, what is going to be a problem is the stress value is greater than 100. So around 135 Newton per millimeter square is going to be happened in the minimum of 50 and 250. So where it is minimum of 50 is, so this one is 50. So at the back height is 50, and the this width is 250, and here is the back height is 50, and feet width is 250. It is elongated it into a 250. So for that scenario, what is getting error is, here is the stress is maximizing the hour limit is the condition should be less than 100 megapascal, but it achieves 135. This is the thing. And also iteration 4. Okay, again the displacement is getting 7, sorry, 0.7. So I need minimum of 0.5, so it is getting 0.7. 7. So this is also getting over value. So for that, iteration 4 it is getting solved. This is the software calculation only, so not a manual. Once I took it run, the multiple number of 11, 12, 13 scenario is taking place. At finally the optimized design will be the same. This one is the optimized design. And where I can, so here we can have a many of a doubts. So I need to take this design back up to my designs, manufacturing, production, plate drawing and all. So here you can go with pack and go with respect to the current scenario. You can take this respective design to the production team. So this everything design will be inside only. Whenever we can open, we can review the results and we can give it to the manufacturing team. This is the optimization tool which is very much useful. Most of the industries were using this. So once I can do a design running scenario of this particular, so the software is getting solved around iteration number 6. So once the iteration number 13 up to it will completed, the optimal result will be shown in this particular area as shown before. I've shown you before that. Okay. Still it is solving. So now it is going around the 8th scenario up to 13. It will run. Once it completed, the optimized design will be there. Okay. Let it be solved. We'll have a recap of this optimization benefits. Okay, so as I said before that the best to find the best alternative design, the optimization is the best tool for the design. Once the design completed, this will be a better one. So this is the two type of analysis study I would like to share you today. So I completed that. We'll have a Q&A session now. So if any questions you can ask now, or you can post it on the chat box. I can reply with you. So that's it.